So, good afternoon, everybody. Welcome to 19 Washington Square North, which is the gateway for scholarly institutional connectivity between NYU New York and NYU Abu Dhabi. My name is Michael Krugenan. I actually serve right now as the interim dean of the Faculty of Arts and Science. But at the summer of this year, I was the academic director of 19 Washington Square North. And part of my job with the great staff here at 90 Washington Square North was many-fold. Some of it was to organize public programs such as these that allowed people to learn more about research that was being done at NYU Abu Dhabi, or just to discuss issues that could be of general interest to the public and to the NYU New York community. And at 90 Washington Square North, in doing that, hosts many such public programs, not only speakers, but book manuscript workshops, musical performances, day academic conferences, and so on. One of the features of making Washington Square North that's distinctive is its Faculty Fellows program. What it is, it's a program where we fund faculty members here in New York teaming up with a faculty member at NYU Abu Dhabi to collaborate on a project over a period of a year in the hopes that it will allow them to continue collaboration for many years to come. Since its inception in the spring of 2020, we have had about 36 now faculty fellows who have done research together between New York and Abu Dhabi. And these fellows have been selected from all the divisions from science, including humanities and social sciences. And the joint research can be a research project or an artistic or a creative project. So today, it's a pleasure to introduce two of those faculty fellows from last year who had completed a year-long project with the project titled Climate Under Construction, Tracing the Heat in Abu Dhabi's Expanding Landscape, which is really a study of the urban heat surrounding Abu Dhabi itself. So the two people who were fellows in this work, one is Yi Yin, who is Associate Professor of Environmental Studies at New York University in New York. So her research examines how climate change impacts ecosystems and communities, focusing on extreme events such as heat waves, droughts, wildfires, and floods. She integrates in situ and satellite observations with modeling tools and investigates the interactions among land, atmosphere, and human systems to uncover how climate extremes propagate through ecological and social processes. The other fellow who actually flew in from NYU Abu Dhabi to be here today is Rita Leal Sousa, who is an associate professor of civil and urban engineering at NYU Abu Dhabi, and also is affiliated faculty with NYU Tandon School of Engineering here in New York. Her research focuses on how construction and urban development interact with environmental processes such as heat, subsidence, and erosion. By combining field measurements, remote sensing, and data-driven modeling, she examines how cities and infrastructure can be designed for greater resilience and sustainability. So today I'm going to talk to you about the project they just completed. So let's get to over to you.
Thank you, Michael, for the kind introduction and thanks for coming. And I will start with setting the stage for the project and also thank you, Rita, for playing the game. And we really want to acknowledge the support of this project and these benefits, which really have inspired us to embark on this journey. And we have been working on several extensions of the projects. And so we will hear sort of like a opening of that and more to come later. So we sort of like, given that we are sharing this talk here in New York City, we wanted it more relevant to the folks. And we were talking about the city urban heat in particular. And it's quite a comfortable day today. So probably urban heat is not something on top of your mind. So I wanted to start by asking you to reflect back of the summers in the past years when we hear all the extreme heat waves repeatedly breaking records in different parts of the world. And I'm sure we have all heard of the word climate change and have a different understanding about it. And it really setting the stage of urban vulnerability in many ways that we will talk later. And so I wanted to start by putting us all on the same page. This is the climate spiral produced by NASA. What it shows is you can envision it as a clock. each cycle is 1 year and with different months at different clocks. And when time travels starting from the 1980s, they have, so the color represents the relative differences of that month's temperature compared to the multi-year mean. And as you can see that it goes wider to the edges, and now turning it, we really can see that from the 80s until up to now, globally, unmistakably, we observe this significant increase. And I think that is something I want to put as a general background of what we are experiencing in different ecosystems. And now zooming into more recent years, here each line represents 1 year, starting from 1940, I think. And the darkest red lines are for 2024 and 2023. Mind you that the red curve, which is marked red, is about 1.5 degrees. If that means something, it is the sort of goal nations agreed upon at Paris Agreement, where we wanted to constrain the global mean temperature rise beyond that. Now, when we talk about climate goals, one single year doesn't necessarily mean a permanent failure, because normally it's a multi-year and like sort of the decadal goal. However, it is a very alarming signal, regardless, that things that was once talked as a future scenario has already arrived, at least temporally. And I think that really is the background of the climate change. Now, sometimes when we say the increase of 1.5 degrees, that doesn't seem a lot, but that is a global average mean temperature across the year. And no one really experience a global mean annual temperature, right? We experience a weather or a temperature at a certain place in a certain time. So what changes is not only the mean, but the distribution. And what's shown here, this plot from IPCC, it shows the distribution of air temperature sort of shifted toward a warmer regime where you have more hot days and maybe like slightly less cold days. And however, another layer that is really important is that it doesn't only shift the mean, but also change the variability. And this, to a large extent, is as the planet warms up, the climate system, the air is able to contain more energy, and so that redistribute heat and water more fastly, which creates more of the extremes. And that is what we experience at a particular time and space. And those extreme events are really most impactful for both ecosystem and society alike. And here, it's an simulation with guided by data from the year July 2024. And as you can see, a lot of places. And that is really, really hot. And to put the scales into perspective, our human body temperature is around 37 degrees. And from a physiology point of view, any temperature that is above 32 is already can create heat exhaustion and heat stroke, and this would worsen when it is humid. And if we go all the way to really the end of the spectrum in the color bar, a lot of the places with significant amount of population are located that has really going into this regime that we need to think. So this scream from monk, I feel like it represents what a lot of communities might have experienced with sort of this extreme heat. And of course, urban adds more complexity into these heat waves already. And we probably have heard about the urban heat island, which this term generally describes that the urban center on average experience a much higher temperature compared to the suburban and the rural areas. There are many reasons to that. The top one is that actually there aren't that much. A lot of the materials for the synthetic buildings, they do not have a very large heat capacity compared to water, for instance. And so the temperature rise more quickly as they receive solar radiation. And then another element is because of the complex geometries, some of the radiations, they just don't really escape And with some changes in the atmospheric concentrations of some like heat absorbing particles, they also warm up more. So that's from the receiving side. Now, it also lost a lot of water body and plant, where evapotranspiration is the most effective way of nature's way to cool down surfaces, right? We all have this experience when you're walking out from a swimming pool, and that sort of like heat dissipation is very immediate. And that process, which in urban places, a lot of places that doesn't have it necessarily, would lost a lot of heat dissipating mechanisms. And if you look at the curves that dipped, there is the park, and where we still have a lot of vegetation, we have these surfaces where water can infiltrate and then be evaporated. And that is one of important urban cooling mechanisms. And yeah, a third element that is us living here, we need a lot of energy, and then we emit them a lot as a waste heat. And all things adding together, the urban centers could be sometimes up to 10 to 15 degrees warmer than the surface. And if we think about the heat waves I just mentioned about, urban really adds on this in a very already hotter layer and then dissipate or cools down much slower. And that brings us into why we care about it, right? So urban heat is not just a form of discomfort. It actually have a severe environmental and social cost of extremes. These three plots are actually created by ChatGPT, and I was chatting with it. How could I make it? I don't want to put a lot of words, and so I think it kind of gets the message out. So for the first, something comes to mind immediately is its impact on heat, and actually, extreme heat is the leading cause of weather-related deaths. And people has like call it the research community has been able to build this sort of excess death estimates as a function of air temperature, and extreme heat is one of the leading factors. And of course, it brings extra stress into our infrastructures for power, water, transport, and also at the same time, it increases the risk of drought and wildfires, and all those things compounding into larger impact. And the third one, relating to economics, it directly result in disruptions into a lot of economic activities, and in particular outdoor laborers like farmers, construction crews, and etc. And some recent study also have looked into during extreme heat events, the crime rates also comes up, which is really all the dimensions. And here are just a few. Okay, by now, I hope I have sort of conveyed what motivated us. And then just clearly, with these two places, with everything being equal, which place do you think would feel cooler? And I guess no one speaks because it's too apparent, and then that's the one on the right side. So the different constructions and different lab covers do create different microclimate updates, and we will get into that more in detail. And another question is, how do we detect the heat? And we all have the experience using a thermometer, right? The traditional ones, it needs to be contacted, and when it reaches a temperature equilibrium, the liquids generally would expand, and that gives us a reading. And in more recent technology, we all have this infrared radar, and where sort of like you point at a place, it magically tells you the temperature. And it's exactly the same way how it is done through satellite remote sensing. And this is in our visible band with night vision enhancement. What do you see here? Anyone care to guess? Oh, sorry? Trees, yes.
The person growing the tree.
Oh, that's really great. I wasn't able to tell the person until I know it, and then my mind knows that a person is there. I can always see. Fantastic. So, and this is just an illustration that, so in the thermal is shorter, the longer wavelengths, which is beyond our visible bands. However, it can tell us a lot of information about a temperature. And bear with me with one equation. I promise this is the only equation that you will see today. And basically, it is a Stefan Boltzmann law. What it says is on the left-hand side, it's the radiance. That's what your thermal radiator or a satellite would see. That is a radiance. And then we have emissivity, which is the efficiency of a surface that's able to give away heat. And then that is the constant, and the T represents kinetic temperature. What is elegant here is that the radiation is the temperature to the force power, meaning that the radiance is very, very sensitive to a temperature change, so that when we observe it changes in the radiance, we can back it out into the temperature. And that is the foundation of how we use the measure a water temperature or what a satellite does. And we can go to more details, and I think we will go to, so one free parameter there is the emissivity. I think that would be some of our future work would focus on. Here is just powering through this is a thermal camera photo seeing the Jersey skyline from Manhattan. And if you have noticed that for each building, there are two sides. One side that is facing south is warmer. And that is where the solar direction, like coming from the south. So for all the buildings, that the south-facing facade is hotter than the other. And of course, the water stays cooler. And this speaks to this heat capacity I was mentioning earlier, that the water, because of syllogism, and it's able to stay relatively cool, even given the same amount of solar radiation. And here is another example. If we zoom in into the urban, and if you look at the left, some parts that is in the shadow are more greenish on the right-hand side. And if we look at the surface of all its things being equal, they are really similar. But this sort of direct exposure to sunlight really shows this large contrast in the temperature, which brings into the importance of having green spaces and to have shades and etc. etc. And now zooming out, when looking at the New York City, we have here three images. On the left, that is in the visible band. In the middle, that is the summer, with warmer color indicating a higher temperature. So this is the Central Park, and not surprisingly, in the summer, the park is considerably cooler as opposed to the more dense buildings. And the opposite is true for winter, because again, the heat capacity of the water, so that the water bodies, the Hudson rivers, stayed warmer in winter, and that sort of shows the different non-cover types important in shaping the heterogeneity of the urban. And here is the New York City on the right-hand side and Abu Dhabi on the left-hand side. Those are two cities by the sea. And this is at exact same scale. So the color bar on both images is 5,000 meters. And so it gives some striking similarities in terms of scales if we consider the key island of Abu Dhabi and that of Manhattan. And there are a lot of differences between these two cities to begin with. They are in completely different kind zones, right? Where New York City is more in temperate. And given the new statistics, actually it can be considered as a soft tropical city map. Anyways, and then for Abu Dhabi, it's more like a desert city. However, they do share a lot of similar challenges. For instance, they are those coastal. There is sea level rise. There is a increased surge of storms and flooding, as well as heat, of course. But because the different climate backset and the urban heat might have very different features, so now that I wanted to invite my collaborator Rita here and to give us more information about Abu Dhabi.
Thank you so much.
Here.
Not the map, you said. So thank you so much. So I'm going to be talking about what we've done the past year on in Abu Dhabi and try to figure out this same phenomena of isolate islands, and it's going to get hot. So, so this is the city. This is our study area. Uh, this is the city of Abu Dhabi, and what you have here in red is our study area. And I wanted to give you a regional snapshot of the region. So the city of Abu Dhabi is located in the Emirates of Abu Dhabi and located in the United and Arab Emirates. The average temperature is around 28 degrees Celsius. Sunshine varies between 8 to 11 hours a day. Very little rainfall, around 42 milliliters per year. So what you have here from here onwards has to do with the Emirate of Abu Dhabi, which is very large, but we'll be just focusing on the city of Abu Dhabi, and it's an hot, arid coastal setting. So what I wanted to show you here is the urban expansion of Abu Dhabi in the past decades. And you can see here the city on the left. You can see a time lapse from Google Earth of the city. Oh, this is going too fast. Of the city changing. And on the right, you can see I wonder if I can play these settings. So I will just go back. All right. So on the left, you see the regional snapshot. You will see the city expanding inward and along the coast. And then on the right, I want you to look over here where my cursor is. And you're going to see, this is a zoom into the island of Abu Dhabi. You see all these islands. So you see that the city has not only expanded inland and along the coast, but also there's been a lot of reclamation and expanded seawards. So the previous slides show you a snapshot and how the city has expanded and grew, and also it shows you the pattern of that growth. For us to be able to relate that with climate change and urban inhabitants, we needed to quantify growth. And so what we have here is a quantification of what we saw previously. Abu Dhabi's urban area has grown more than threefold since the 1970s, since its origin, and has added roughly 10 Manhattans to the city, so the area of Manhattan 10 times. Most of the expansion has occurred inland towards desert. And what you see here, each color of the graph here shows marks and not a decade of growth, but a period of growth. And so the city started here in the island of Abu Dhabi, concentrated, and then it started expanding towards the inside and along the coast. And the gray and the pink are the latest spurts of growth. So this has become one of the fast growing urban landscapes. We also wanted to look not just so we wanted to quantify not just the growth itself, but we want to quantify how different types of land have changed and what has changed throughout these decades. So we looked also at coastal transformations. And what we see in this map here is reclamation from the 70s all the way to 2024. And since the 70s, new land has been reclaimed, roughly 2 times the size of the city of Paris. That's more or less four Manhattans throughout these 50 years. There's also several islands that have been built, like those ones here in brown, and also here along the lagoons. And there's been a lot of these islands have been connected through bridges, and this has created a continuous urban coastline, which was previously just several islands that were isolated. So this expansion, we saw the expansion before towards the desert, and now we see here this expansion seaward towards the coast, reshaping all these lagoons and the canals. So I want to give you a zoom, a close-up of, this is the island of Abu Dhabi. And it shows a little bit of this dynamic. It's not just land that has been reclaimed, but there was also land that has been dredged, right? So there's been soil erosion, and so land that became water, but also land that has been dredged. So there's been, throughout these 50 years, a moving boundary between the sea and the city, where land has been reclaimed, land has been removed. And here in red, you see all the reclamations. This is the Abu Dhabi's Corniche. So this is the historical center, let's say. And also you see a lot of the some of the dredging that has occurred to build ports and so on. And this is just one example. You see this all across Abu Dhabi. Important is also vegetation covers, and we wanted to look at what has been, or quantify what was sand and what was mostly desert and what has become green throughout this decade. So what this map shows is the green areas that have been added in from the 70s all the way to 2024. And so you see that the green areas have multiplied almost fourfold, right? And you see that the first editions are the ones in yellow, and they follow urbanization, and those initial vegetations have to do with landscape of urban areas, and that later on, those darker colors are mostly related to mangrove restoration initiatives. And mangrove is a local species. It's a small tree, a scrub that is native to the region, and that grows in the very salty environments and along the coasts. We then, after we classified all these changes and quantified all these changes, we look at the line surface temperature patterns. And here you see the maximum land surface temperature in 2023. And what's very cool here, is very interesting here, which is a little bit different than what happens here in New York and in Abu Dhabi, in Manhattan, is that in fact the areas that have been urbanized are slightly cooler than the areas that are deserts still, right? So you see the yellows are lower temperatures, these are in Celsius, and the reds are higher temperatures, and that has mostly to do with the addition of vegetation to what was sand before, and to the addition of canals and lagoons. Here we have some trends for the past decade, and you see, and these are the times of the maximum land surface temperature, and you see some cooling effects at certain areas, as well as some heating effects in what is mostly the desert areas surrounding Abu Dhabi. And then finally, this is the trend that we got for the medium LST, and you see a lot of, on average, a lot of cooling for that basically maps to the urban areas. This is a comparison between the land surface temperature in Abu Dhabi and the land surface temperature in New York. The scales are a little bit different, so mind you that, right? This is maximum land surface temperature. These are 65. The very raw hot spots are 65 Celsius. This is almost, I don't know, 150 Fahrenheit. So this is pretty hot, and they occur mostly in the desert areas. And then the city areas actually cooler. And then you have some urbanized areas that are hotter, like Musafa, which are industrial areas with very little greening and very little canal. And then when you look at New York, and the scale here is from 30 Celsius to 50 Celsius, and you do see, you clearly see the cooling effect of Central Park here in the middle, where the cursor is, and you do see parts of New Jersey to be very, very hot, as well as certain areas where in Manhattan that are also quite hot. So some hot spots, both in New Jersey and in Brooklyn side. So we wanted to also look at the trends, right? We what I show you are spatial distribution of this LST, and also spatial distributions and quantifications of urban changes and land cover changes. And so we wanted to correlate land cover types and changes with temperature changes, right? So we looked at 4 categories, and they are here: constant urban, so areas that remain urbanized throughout the 10 years. We looked at areas that were sand and became inundated. Don't love the term, but that became water. And then we looked at areas that were land and became urbanized, so mostly was desert and sand that became urbanized, and we looked at reformation. And what the graph says, and this spans from 2014 to 2034, and what we did was we took representative samples or polygons along those maps that I just showed you. And what we see is that urban areas remain the hottest, right? They reach the highest summer peaks, and they also show the largest seasonal swings, so the largest difference between summer and winter. Reclaimed land and water adjacent zones stayed cooler overall. That's the reds here and the yellows. Even though what we saw for these samples is that the temperature is rising on average for those 2 classes of land, and this annual rhythm repeats steadily, and then but over time, what we're seeing now is that that there is a narrowing between land types, particularly between reclamation and inundation. You see that the highs and the lows become almost overlapping when there was somewhat of a difference in 10 years ago. We also looked at vegetation, because we've seen that vegetation has a direct correlation with the cooler temperatures, and we wanted to see we wanted to quantify those effects. And so we looked at 3 types of transitions, or 3 types of categories. We looked at areas that were constantly non-vegetated from 2013 all the way to 2014, areas that were constantly vegetated, and areas that went from that were planted or went from non-vegetated to vegetated. What we have here is an average for all the Januaries for the 10 years, all the Februaries within the 10 years, the Marches, and so on. And what we saw, as these preliminary results, what they show is that green areas stayed cooler, about 3 to 5 centigrades, especially during the summer months, right? In the summer months, you see a bigger difference between green areas and non-vegetated areas. Bare or built-up zones, they are the ones that heat up the most, and they remain hottest all over the year. And then newly planted sites are the ones that show the more cooling or more cooling throughout this period. And I have to say that at those samples that we pick, the conversion occurred at different times in between those 10 years. So and then finally you see that this cooling gap narrows in the winter, right? That the averages become much closer than in the summer, and that's because shade and evapotranspiration matter less in the cooler months. Even though Abu Dhabi is quite hot, it does get cold in the winter. We looked then at NDVI. We wanted to quantify vegetation. When NDVI is a vegetation index that allows you to basically quantify how healthy the vegetation is and how dense it is through satellite data. And we wanted to do that because gives us a number that we then can correlate with LST, which is another right? Instead of having a category vegetation or vegetation, we have now an indication of how dense and how healthy that vegetation is. So typical NVDI ranges are vary from the typical. So typically, the higher the NDVI, the more vegetation and more dense and healthy vegetation you have. So from 0.6 to 0.9, you have dense, healthy vegetation. 0.2 to 0.5, you have sparse, more stress vegetation. Abu Dhabi lies, vegetation lies more over here. And then anything below 0.2 is just bare soil or water. So we wanted to do that. We want to quantify this vegetation health from and concentration, densification, and then compare that with the LST. And that's what we have here. We have two maps. One for 2014. We have NDVI for June 2014, and then LST in June 2014. And what we see is striking. We see that. If we look at lower values of NVDI, which are these lighter colors, they correlate with higher values of LSC. And the contrary is also correct. It's also true, right? Higher values of NVDI correlate spatially with cooler areas, so lower values of LST. And we then looked at, and then the same year, this is actually been a very, there's almost very little vegetation in this area, even though it's highly dense urban area, but it's mostly an industrial area. You see, it's very, very hot. We then, this is now a snapshot of a year ago. And what we see is, we see the new islands showing up. We see also the vegetation becoming more dense. And we see the same patterns. We see the vegetation expanding along the reclaimed and managed coastal zones. And then we see the same pattern. High NDVI, low LST, low NDVI, higher LST. So exact same pattern of what we saw before, but however, we have denser vegetation areas, and we also have higher temperatures. This graph shows the quantification of what we saw before, and what you see on the left is the NVDI trends through different categories, the different categories that I just showed you. So constantly non-vegetated areas, constant vegetated areas, and areas that went from bare land to vegetation. And so in blue, you have these constant non-vegetated areas, and what has happened is that, NVDI remained constant, no vegetation, makes sense. And this is an average per each year from 2014 to 2024. And you see the LS3 trend going up, right? So the land surface temperature going up throughout the years. For constant vegetated areas, we see that they have somehow NVI has increased. That has to do with the densification of the vegetation and maybe replantation. And you see a little bit of an increase. It's almost flat, but a little bit of an increase of the LST. And then this is the most striking. These are areas that went from non-vegetated all the way to vegetated. And you see the NVDI increase the most, but you also see the temperature, the land surface temperature decreasing the most. All of those are statistically significant, except for this one, which the slope is 0, so that makes sense. So we see an inverse pattern between NVDI and LST. Areas that greened, they cooled, and areas that remained bare, they heat up. So it's not just vegetation that matters, but also the materials that we use in our cities. And this picture somewhat shows a little bit of that. This is a thermal image of the Chrysler building and shows how materials that have different albedo. Albedo is a characteristic of the thermal characteristics of the materials, and it quantifies the amount of light of sunlight that gets reflected. And so you can see that darker facades have lower albedo and absorb more heat. You show in red and hot. And then you have metallic roofs like the roof here. There's almost, you cannot see it, that have high albedo reflecting sunlight, and they remain cooler at cooler temperatures. So in these benches over here. So these images shows you that the materials that we use and materials that we use in our construction do also are also very, very important when it comes to this issue of temperature. Now, I wanted to also touch a little bit about these mitigation measures and make a parallel between what's done in Abu Dhabi and what's done here in New York. Most of the infrastructure, the green infrastructure in Abu Dhabi, is nature-based, and so we have all of these, mostly as through mangroves. And what we have here is the example of the Jubail Mangrove Park, which is a really large-scale nature-based solution for not just heat moderation, but also it protects the shores, and so it has this multi-function form. So most of mitigation measures come through this nature-based colleague. And then there's been an incredible emphasis on revegetating mangroves of Abu Dhabi, whether that is by foot or by drones. And what you see here is that some of these vegetation initiatives on the left by foot, and then on the right using drones to plant millions or to drop millions of seeds. And since 2020, over 44 million of mangrove trees have been planted in Abu Dhabi, and the goal is to plant much more by 2030. Now, in New York City, we do also have some nature-based cooling initiatives, so like the Central Park. However, because the city is already so much built, a lot of the strategies in New York are engineered green infrastructure. So projects like the highlight that you have here on the left and the Shabi Center green roof on the right, they integrate vegetation into the built environment to reduce temperatures. And they also are multifunction. They not just reduce temperature, they manage stormwater, they enhance air quality. So a little bit of different strategies, also different spatial distribution. So because in the mangroves only grow by the coast in Abu Dhabi, most of those barriers and those little living lungs in Abu Dhabi are around the coast. And here in New York and other cities, that infrastructure is just scattered inside the city, just integrated with the city. Now, all the work that we've done so far, or done the past year, has been by using free satellite data, Landsat, and Landsat has 100 by 100 resolution. So that does not allow us to look at any fine scale temperature variations that come up from localized green spaces, surface materials, all of these things that we're talking about, shading, moisture conditions. So we started this summer. This summer we started collecting some data, and we did that. We did a few campaigns. We stopped when it got very, very hot, and we thought about other ways of doing these campaigns. And we started in the back we started our campaigns near Abu Dhabi, New York University Abu Dhabi campus, which is here, located here. And we went and we chose this area, one, because it's close by, but two, because we could find many microclimates around New York University. We had bare sand, we have roads, we had somewhat of a wild environment, even though if it's not very dense. And we even had mangroves, and we had water. So we went about doing some preliminary field measurements, and these are just a few points. I didn't want to bother you with a lot of data, but what we saw was striking. We saw a lot of contrasts that were linked to material, to moisture, to vegetation. We measured on the asphalt, we measured on the sand, both wet and dry. We measured within the mangroves, and we find quite striking differences. The asphalt surfaces recorded the highest temperatures, and the wet sand and the mangrove shaded areas were cooler, up to 10 to 15 Celsius, which is a lot. And then we compare that also with the maps that we have from LST, and we saw that the satellite values were giving us systematically higher values, and we're still looking into this, but we believe it's due to this mixed pixel average, and we're talking about completely different resolution. So what we see is that the results show that there are these striking differences, and that it is important, if we really want to look at microclimate variations, to actually go on in the field and measure these variations, not just during the time that the satellite passes, like we did here, but also throughout the day and throughout the years and the seasons. This is just some of the images of the areas where we collected measurements. We use handheld thermistors, which are just thermometers, and infrared sensors, and we collected across the asphalt and across some landscape, some vegetation from landscaping, wet sand and dry sand, and then also within the mangroves. Finally, I wanted to just show you what the infrared. So I showed you before, what I showed you here was this is the thermometer, the temperature on the ground. This is a 1 point, and then this is what the infrared sees. And we see here, mind you, that the yellow colors are hotter, and then these dark colors are cooler. So we see here the sand. The dry sand, much hotter than the surrounding environments. This is a picture or a measurement. This one is a measurement by the water, by the mangroves. You see the water much cooling, having this pooling effect throughout the day. And then this is within the mangroves, and you see this is the coolest that the temperature gets, and this is under the shade of the mangroves. So sands heat up faster, water cools down slowly and stays cool throughout the day, and then the mangroves are under the shade are stay deposed. So we wanted to leave you with maybe 3 points of what we've learned the past year and what this project in Abu Dhabi taught us about urban heat. And the first one is that the way we build literally redraws the city's climate. So the urban form, the land reclamation, the materials that we use, they don't just shape the skylines and what we see, but they will shape everything: the wind, the moisture, the temperature. So every new surface is going to have somewhat of a consequence, a thermal consequence. Green and blue spaces are still the ones that remain the coolest or cool the best. Vegetation and water, that's what we've seen. And they are our strongest defense against the heat. They moderate temperature, they store carbon, and they make cities more livable, even in extreme climates like Abu Dhabi. And the nature is not decoration. So it's climate infrastructure. So green infrastructures like, parks here in Manhattan, mangroves in Abu Dhabi, wetlands, green roofs, they aren't just side projects. They actually are systems that are going to help us regulate the city's heat and protect coasts in the case of the mangroves, and help us sustain or build sustainable and resilient cities. And then finally, I wanted to thank some of the people that has done a lot of the work. Bassam Dahi, who is our postdoc in New York University, Abu Dhabi, is done a lot of the remote sensing processing. Kathy was an intern, undergrad intern for a few weeks. She helped us also with some of the data processing. Iana just joined. And then Prashant Marpu and Stefan have from Space 42, which is a UAE space tech-based company, have been instrumental in helping us access data and even collecting data. And so we want to thank them. Otherwise, this work would not have been possible. And I want to thank you as well for being here. And we are happy to answer any questions that you may have.